Okay, continue on our subject today, Bioreactor Engineering. We will continue on this lecture. This setup lecture is the last set already, and then today I will focus on heterogeneous reaction. So I will introduce you heterogeneous reaction. Heterogeneous reaction is simply like you have more one phase in your system. You have solid, liquid, for example, and then we will talk about the internal mass transfer. This one is the modulus, the T modulus, and effectiveness factor. And then after that, after internal is external, and then we have liquid solid mass transfer correlation, and we will discuss on general comment on the bioreactor in heterogeneous reaction, especially in bioprocessing. And let's start today. We have, this one is the picture of heterogeneous. You have more than one phase, as I told you. This one is immobilized cell. This one is gel particle. This one is immobilized biocatalyst. Cell entrapped into a soft gel, for example, and then we have internal surface of the porous is the B. It's different. This one is the cell entrapped with the gel, and then they have this one. You have porous like this. You have again you have layer here. This is a biocatalyst, and then you have a concentration profile. And then it's lower, and then it's become very low here near 0. Okay, and then it's R square. And if the cell do not, this one is we call immobilized. So we move, we make the cell stick together, and then not stick together. We make the cell not moving, something like that. So it's called immobilized cell. Okay, let's move to the one. And then we have two things: external mass transfer and internal mass transfer. Okay. Bulk liquid across to near the surface, like this one. This one is external mass transfer. Internal is inside the particle. Mass transfer to solid is required. Okay, this is the difference between external and internal mass transfer. You can have a look like this. And then we have this one is a picture. This is profile. Sometimes profile is different because sometimes it's connect like this. Sometimes it's doesn't connect. It's move a bit higher. It's different. Okay. And then this is the scenario. The staff at the core of the first surface, and then this core is this continuity of this concentration is had a gap here, and then the C is attached to solid liquid, for example, and then this one is liquid solid interface, for example. Okay, sometimes it's connect, sometimes it doesn't connect like this. We have something different. Some concentration gradient is different. And then sometimes we have shell balance. Okay, it's written on the book. So we have second order of differential equation in term of R here, and then this one is concentration. This one is occur for reaction rate. This one RA is reaction rate, for example. Okay, we have second order here, and we can derive, and then we have the concentration profile as well. And then we come with the example of this one, and then we just want to work on the example, right? Okay, I explain you example. Enzyme is immobilized. Immobilized is this picture like this. Okay. In 8 millimeter of bead is like sphere shape, for example, diameter, and concentration of protein per shell, okay, is this one, 0.018 kilogram protein per cubic meter gel. 10 beads are immersed in a well mixed solution of this one substrate. The effective diffusibility of substrate in agarose is this one. This one is diffusibility. Kinetics of enzyme can be approximately at first order. This one is a first order with this is a K constant. Mass transfer effect outside of the particle are negligible. Okay, then we need to plot. We need to find the profile here like this as a function of the particle radius. So we need to have this kind of thing is a radius. Okay, we need to solve equation anyway. Okay, with the solution R is from this one. This is diameter. R is 4 millimeter. This one is diffusibility. This one. And okay, concentration AS at the surface is this one. Okay. And from the diameter, we found the volume of the bead is a square. Is a square shape. So it's look like this one, and then this is one is a volume of this one. 10 bead. We term this one as 10 to the minus 6. Okay, it's from 10 to the minus 7 here. And then we have this one, K1, and then this is the one that we try to find from this equation. R K1 diffusibility is this one. Okay, then this is a K1 is the constant for rate of reaction. And then we have this one, CA equal to this one. This is a definition of hyperbolic sine is this one. So we calculate this to this one. And then we have equation. Okay, we need to have a look on, and then from the text, so we can plot this one. So it's a radius. This is at the surface. and then it's down to this one. So we need to have a look on equation, this one and this one as well, and then we substitute on this. Okay, I will insert the equation here, and then we move to the other example. So okay, we need equation in this one. Non-viable yeast cell. Viable is living cell. Okay, yeast cell are immobilized in alginate bead. Okay, so we put in alginate bead like this one. And then what next? The bead are stirred in glucose media under this with oxygen, without oxygen, anaerobic. The effective depend on cell density according to this one. This one is cell density. Weight fraction of the yeast, this one. Okay, the rate of glucose consumption as can be 0. Okay, can be 0. The reaction rate at yeast is percent weight. Okay, and then of the bead is this one. Okay, reaction rate is this one, 0 order. Catalyst utilize effectively. The concentration of glucose inside the particle should remain above 0. The concentration of glucose, okay, the concentration of glucose is above 0. Okay, the first thing is plot allowable particle size as a function of bulk glucose concentration between 5 and 60 gram per liter. The medium contain plot Rmax. Plot Rmax as a function of the cell load between 10 and 45% weight. We have two questions. The first thing is we put this one. This is yeast 5%. Okay, yeast percent YC. And then we calculate diffusibility of this one. Okay. Convert to kilogram. Okay, we convert K0. This is a constant to kilogram. And we calculate the Rmax from 13.7. Okay. Do we have to, can we still access it? Okay. 13.17. Okay, 13.17. Where is it? And this is one that we look for. Okay, this is a function, so we can have a look on this one. X is changed to R, and then this is the equation that we look for. And 17, where is 17? 17 is this one. This one is Rmax. Okay, we change this one to Rmax. 17, and then what else? We have Rmax here. From what? From 5 to 60. Okay, and then we have Rmax here. And then we plot Rmax here as well as a function of Ca. Ca is concentration to the bulk. This one. Okay. Next, we have Cs is this one, and then we have Y concentration of yeast as a series, and then we have dA diffusibility, K R effect, and then the Rmax is changed. This one is Rmax is changed because we change the concentration of the yeast here. And then we plot this one as a function of Rmax as a function of this is reduced. If you are reduce your if you increase your cell concentration, your Rmax will decrease. But if you increase your concentration of what glucose concentration, if you increase, so your Rmax is increased as well, like this one. But on the other hand, if you increase your yeast concentration, your Rmax is decreased. And then we move to the thrive modulus is this one, phi, and then it's written on this form. So we have many factors, but we have again diffusibility, rate constant, and then this one is concentration. Okay, and then it's become like this. So sometimes we just look at the plot, for example, and then what is the thrive modulus, two modulus, what is it? And again, is immobilized enzyme. Invertase is immobilized. This is the name of the enzyme. Is immobilized in anionic resin. Average diameter also is diameter is a sphere 1 millimeter. The amount of enzyme inside the bead is measured by protein assay. Okay, we can measure the protein concentration of the resin. A small column reactor is a column reactor is packed with this bead. Okay, 75 ml of sucrose solution is pumped rapidly through the bead. In another reactor, an identical quantity of free enzyme is mixed onto the same volume of sucrose concentration. The kinetic parameter for immobilized can be assumed to be equal to the free enzyme. Okay, we have two terms here, the immobilized, which is this one, the one that I show you. So you have gel and then you immobilize it. This one, if you don't have a gel, is called free cell. For the free cell is this one. The turnover number is this one. Okay, effective diffusibility is this one. And reaction rate for free enzyme and immobilized enzyme. Okay, this is the work of invertase. The enzyme is the biocatalyst, so it's help the reaction occur, but it doesn't it doesn't change when the reaction occur. So from sucrose you change to glucose, and then you have fructose. And then this is how you produce glucose from fructose. And from the data, so you change the unit. First is a km, and this is a diffusibility, where you just change the unit, and R as well. And what else? CAB. Assume CAS is okay at the surface is equal to bulk concentration, and then we change the unit. Mass of the enzyme you multiply with this volume is this one. The free enzyme concentration is this one. Okay, this is Vmax. Vmax is this one, so you just change the number. Okay, and after that you put in Michaelis-Menten equation Vmax CAB Km KAB, okay, is this one. The multiply by liquid volume give you total rate of reaction is 1.55 times to 10 to the minus 6 gram mole per second. This is the free enzyme kinetics. Okay. For heterogeneous reaction, Vmax is X placed on catalyst volume like this. So you multiply everything of the resin. And then we have beta and phi m. We have phi m here. Okay, you have beta first 0.55, and then we have from the table, okay, it's quite complicated, so you put everything here, you find phi m 0.71. Okay, and then you have a figure of this one, and then we use equation. Is really complicated. Okay, and after that you have phi 0 0.72. 0.72. Okay, and then we have phi 1 1.4. Okay, and then you need to refer to the textbook here as well. Okay, the for kinetic enzyme is this one. Okay, is nearly the same, right? Okay. Okay, you can pause this one and then have a look and then work it on it. This is a immobilized cell. As the kinetics parameter we assume to be equal, this is the same rate as found in the free enzyme. It's the same rate. It's the same rate. No matter we have quite long equation, it's the same because we have assumed it's the same things. The effectiveness factor indicate that the rate reaction immobilized is 75% of occur in absence of mass transfer effects. Okay, so the total rate of immobilized cell is this one. Is lower, is 99% of the free enzyme. Okay, we have this one, and then we can have a look later. Okay, what else? Okay, we have more. We have number 4, internal oxygen transfer. Okay, baby hamster kidney cell. Okay, is a animal cell immobilized again. Notice that is all is immobilized because it's heterogeneous reaction. Average diameter is 5 millimeter. Okay, bulk concentration is this one. This concentration. The rate of oxygen is consumption is this one per catalyst. Okay, and then this is diffusibility. Okay, assume at the surface is about it's the same concentration. Oxygen uptake can be zero order kinetics. We have two questions here. Are internal mass transfer significant, and what reaction rate are limited? Okay, we have table here, and then we have phi r over 3 square ra observed, and this one diffusibility, and then concentration at the surface, and then r is this one 2.5 millimeter, and then we pack everything here, and then we have phi 3.9, and then for sphere catalyst, and then we have a look on wait figure here, this one. Then we put in, this is the rate of reaction without diffusion heuristic. Okay, this one without internal mass transfer, without internal mass transfer. Okay, is 2.1 times 10 to the minus 4 kilogram per sec cubic per cubic meter of catalyst. Okay, it said are significant. Okay, from this person. Okay, we have need to check this one. So this is significant. This is significant, and then this is the rate without diffusion restriction is this one. Okay, we have to move to the final example, number 5, bacterial disinfection. Okay, denitrify bacteria are immobilized, again immobilized, and used in CSTR stir tank reactor for removal nitrate from groundwater. Okay, the nitrate concentration is 3 gram per cubic meter. Conversion rate is this one, 0.01 of catalyst. The effective diffusibility, this one is diffusibility in the gel, in immobilized gel, and the gel is 6 millimeter in diameter, and the liquid mass transfer coefficient is this one, km. For the kinetic is approximately this one. Okay, we have 3 questions. Does external mass transfer influence the reaction rate? Are significant or not? Okay, and okay, okay, we have R here from 6 to 3. Okay, 6 millimeter to 3 millimeter. Table here for sphere. Okay, okay. External this omega is quite large, so external mass transfer are significant. Okay, and for this one, and phi is 0.9, significant also, as is phi more than 3, similar to this one, 3.9, and then again this one 3.9. So internal mass transfer also important. Okay, and then we have to calculate new CAS. Okay, 6.3, and then we have sphere, and then we have figure this equation. This is the rate. If the internal and external mass transfer resistance were eliminated, the reaction rate would increase by 7.7 times. Okay, from that one to this one is increased a lot. It increased a lot. Okay, we have a look on how external mass transfer important or not, and then internal mass transfer important or not, and then we check the thing here. And for more common or bioprocessing in the heterogeneous reaction is aerobic reaction mass transfer oxygen is more. Okay, because we need oxygen, is likely to limit the reaction rate. Okay, than other substance. We have relationship between internal effective factor and concentration gradient, and we have internal and external mass transfer limitation. Okay, and then we have operation of catalytic reactor. For this chapter, we know how heterogeneous reaction based on immobilized. Many things we talk about immobilized. We have observed and true rate. Okay, and then we have a phi here. And for the next one, we need to sum up what is bioreactor engineering in our sense. In the meantime, I have assignment for you already to work on. So hope you enjoy my lecture, and then we continue on to the next lecture, and then we nearly to finish the course. Okay, enjoy your time.